Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit number 3, Lesson number 7 on more work with parallel lines. So in the last lesson we reviewed the properties of parallel lines and then we went on to do some important work with both problem solving and proof. Specifically we looked at the proof that angles on the same side of parallel lines on the interior, same side interior angles are supplementary, they add up to 180 degrees. And we also proved that the sum of the angles of a triangle was also 180 degrees. A lot of 180 degree things. All right. To begin this lesson, I'd like to review the major properties of parallel lines, both from the last lesson and importantly from the last lesson's homework, because there was a very, very important problem there. So let's get into those properties right now. All right, review of important results from parallel lines. Let's go through them. All right, result number 1. When parallel lines are cut by transversals, alternate interior angles are equal and corresponding angles are equal. All right, so in other words, I've got these two parallel lines cut by a transversal. Alternate interior angles like 1 and 2 are congruent, and corresponding angles like 1 and 3 are also congruent. All right, simple enough. Property number 2. The sum of the measures of the three angles of any triangle is always equal to 180 degrees. That's right. Any triangle I put up here, this one's got a 105 degree angle, a 25 degree angle, and a 50 degree angle, those will always add up to 180 degrees. Again, a direct result of parallel lines. Now, the next property is one that you were supposed to figure out on the last homework. Now, this is important. You know, sometimes students do homework, sometimes students don't do homework. Very often, homework, at least that we write at eMathInstruction, will include important results that you're then supposed to carry on to other lessons, and this is one of them. Specifically, an exterior angle of a triangle is the sum of its remote interior angles, and therefore it must also be greater in measure than either of its two remote interior angles from the homework. Now, what does that mean exactly? And we're going to look at this in the first exercise. But whenever I have a triangle, if I take one of its sides and I extend it, that then creates an angle. And if this angle is 150 degrees, well, what that means then is that these two angles will add up to be that angle. That is such an important result that not only did we have you work on it in the homework, we're going to sort of verify it in the first problem that we look at. So let's jump into that. All right, exercise number 1. A triangle is shown below with its sides extended. All angles have measures as shown. Calculate the value of the exterior angle at each vertex and verify it is the sum of the two remote interior angles. All right, so in other words, I've got this triangle and each side I've extended and that creates new angles. Now, we can calculate the value of each one of those exterior angles by simply subtracting from 180. Here's what I mean. Let's take a look at angle 1. What we know for certain is that these two angles must sum to be 180 degrees. So I can easily take my calculator out and do 180 minus 34, and I'll end up getting 146 degrees. That's got to be the measure of angle 1. But now I can clear my calculator and verify that when I do 83 degrees plus 63 degrees, I also get 146, right? These two angles sum to be the measure of angle 1. Any exterior angle will always be the sum of the two remote interior angles. Take a moment now, pause the video, and verify that for the other two exterior angles as well. All right, let's just do one more I'm going to change my pen ink really quick. Let's do one more together, and then we'll leave the third one, because it gets to be a little bit redundant. So for instance, if we were taking a look at these two angles, right? If I want to know the measure of angle 2, I'll just do 180 minus that 83 degrees, and that gives me a 97-degree angle for angle 2. It's got to be 97. Now what I'd like to do is I'd like to take these two angles, that 63-degree angle and that 34-degree angle, add them together, and I also get 97. And again, it makes sense. If you didn't do the problem from the homework, it was the last one on the last homework set, the basic reasoning is simple. These three angles must add up to 180. They have to equal 180. These two angles also have to add up to 180, right? So kind of using a subtraction argument, right? If I subtract the angle up here, the 83-degree angle, right, from 180, what remains has to be these two angles or that angle. So they've got to be the same. All right. Now that is an important fact, and we're going to need it as we move forward, okay? The reason being is that we want to be able to prove that two lines are parallel. So there's kind of two pieces with parallel lines. In one situation, like in the last lesson, we know two lines are parallel, and then we prove stuff from that. In the other situation, we know things and want to prove that two lines are parallel. And there are going to be two major ways we will prove that two lines are parallel. Let's take a look at them now. Proving lines are parallel. One way will be to prove that two lines are parallel if any pair of corresponding angles are equal. So we know that when lines are parallel, corresponding angles are equal. The converse is also true, meaning that if any pair of corresponding angles are equal, the lines must be parallel. Likewise, method number 2, two lines will be parallel if any pair of alternate interior angles are equal. Again, the logic one way is when two lines are parallel, alternate interior angles are equal. But the other direction is if two alternate interior angles are equal, the lines are parallel. All right. Logic can be a funny thing. It doesn't always work that way, right? Think about it this way. If it's raining outside, the sky is certainly cloudy. But if it's cloudy outside, it doesn't mean that it's raining. But these two things really are sort of two-way roads. If lines are parallel, corresponding angles are equal. And if corresponding angles are equal, lines are parallel. Same thing with the alternate interior angles. Now, what we're going to do in the next exercise is we're going to actually prove that when two corresponding angles are equal, the lines must be parallel. And we're going to use a technique that we're not going to use a lot in this course, but it's what's known as a proof by contradiction or an indirect proof. All right? So let's take a look at exercise number 2. Exercise number 2. We will prove the first theorem using an indirect method of proof. We will assume that two lines that have corresponding angles, that have equal corresponding angles, very important, are not parallel, and see what happens. Okay? In other words, we're trying to prove that if two corresponding angles are equal, the lines must be parallel. So what we do is we assume the opposite of what we're trying to prove, i.e., we've got a pair of corresponding angles equal, but the lines aren't parallel, and we're going to see just what happens. All right? In the following diagram, all right, non-parallel lines, M and N, have been cut by transversal R to form angles 1 and 2. Now keep in mind, what makes two lines not parallel is that they intersect. That's amazingly important. Two lines are not parallel if they intersect. So I've got this line M and this line N that intersect out here at point C, okay? And I'm claiming, okay, that angle 2 and angle 1, which are corresponding angles, right? They're in the same place on those T's, right? I'm claiming that they're equal, okay? But that the lines aren't parallel. So letter A. Why does this scenario contradict what we know from above about exterior angles of a triangle? Think about this for a moment. Why is it that this somehow contradicts what we know about exterior angles of a triangle? Think about this for a minute. All right. Well, what we learned about exterior angles of a triangle is that the measure of angle 2, which is the exterior angle of this particular triangle, right? That the measure of angle 2 must be equal to the measure of angle 1 plus the measure of angle 3, right? That's true of all triangles, all triangles. The exterior angle must be the sum of the two remote interior angles. But that would be weird because the measure of angle 2 equals the measure of angle 1. And that's what we've said, the corresponding angles in this case are equal. But if the measure of angle 2 is equal to the measure of angle 1, then either, well, not even either, then the measure of angle 3 would have to be 0. Right? That thing can't have any value. Plus, we know that the measure of the exterior angle must be greater than these two angles. And therefore, it contradicts something that we've already proven, which is that the exterior angle always has to be equal to the sum of those two remote interior angles. Well, what does this tell you about two corresponding angles that are equal? Well, it means that the lines that created them cannot intersect. Right? So in this case, line M and line N, the lines that created angles 2 and 1, along with the transversal, of course, those lines can't intersect, because if they do intersect, then those corresponding angles can't be equal. Well, the lines that created them can't intersect, so must be parallel. All right? And that's kind of a neat result. Again, it uses a method of proof that really is what we call indirect. In other words, we assume, right, the opposite of what we're trying to prove. See, we're trying to prove that if these two angles are equal, then these two lines must be parallel. And we say, all right, well, let's just say these two angles are equal, and these lines aren't parallel. Of course, what it means for these lines to not be parallel is that they must intersect. But now if they intersect, these two lines plus the transversal must, whoops, that's interesting, must create a triangle. In fact, they must create this triangle, the one that I accidentally moved. All right? And because of that, then that angle, that exterior angle number 2, simply can't be equal to number 1. And therefore, the lines could never have intersected in the first place. Whew. Well, I'm hoping you followed that. But at the end of the day, the most important thing to understand is that if we know that two corresponding angles are equal, the lines that created those angles, along with the transversal, must be parallel. Likewise, what we're not going to prove for now is that if two alternate interior angles are equal, then the lines that created them also must be parallel. All right? So, let's keep going. Okay. Exercise number 3. In the diagram below, lines P and S are cut by transversals. The angles are marked as shown. Explain why P and S must be parallel. Okay? So again, it's not a proof per se, but it's an explanation, which is sort of like one level below a proof. Take some time and think how you would justify that P and S must be parallel. All right. There are a lot of different ways to do this. Okay, we could choose alternate interior angle pairs, or we could choose corresponding angle pairs, and maybe I'll take a look at both of them. First, let's go the corresponding angle pair method. Now, we know, because this figure is a triangle, that the missing angle here, right, can be calculated by simply taking our 74, adding to it our 43, and getting 117. That's the sum of those two angles. And then I can do 180 minus 117, and I get 63. So, if I erase that, then I know that angle must be 63 degrees. But now, getting rid of this, I can say since two corresponding angles are congruent, P and S are parallel, right? This angle and this angle are corresponding angles. Specifically, corresponding angles, and it's a little bit difficult because you've got this extra line in there. If you could kind of block out this particular line, or just throw that triangle out of there, if you can block out this particular line, then it's very easy to see that this angle and that angle correspond to one another. All right? On the other hand, we could also look at this from the perspective of alternate interior angles. So a totally different way of looking at it, right? Let me kind of get rid of this 63 really quick. Okay, because these three angles must sum to 180 degrees, we could do the same idea that we did before. We could take the 63 and the 74, and we could add them to get 137 degrees. I won't even use the calculator for that. We could then do 180 minus 137, and we'd get 43 degrees. So this angle would have to be 43 degrees. But now, that angle and this angle are alternate interior angles. And we could make a statement very similar to this. We could say, because two alternate interior angles are congruent, the two lines must be parallel. Okay? So it's really kind of a nice relationship between these corresponding angles or alternate interior angles and parallel lines. If lines are parallel, alternate interior angles are congruent, corresponding angles are congruent, and conversely, if corresponding angles are congruent or alternate interior angles are congruent, lines must be parallel. Okay, let's keep going and use those facts now. All right, this is cool. Now, we're going to kind of combine those facts all in this one simple proof. Okay, let's take a look at it. Exercise number 4. In the following diagram, A is parallel to B, and B is parallel to C. Prove that A must be parallel to C. Now, this probably makes all the sense in the world. I mean, if I know this line's parallel to this one, and this one's parallel to this one, I'm trying to prove that this one is parallel to that one. It seems like it would make complete sense, but then again, there's nothing about parallelism, i.e., two lines not intersecting, that would say, well, if these two lines don't intersect and these two lines don't intersect, then these two lines don't intersect, right? There's nothing about that necessarily that follows, right? But watch the logic here, okay? Actually, maybe take a moment and think about the logic. We're going to write this one out as a paragraph proof in a moment, but take a look and think about what we've been talking about and see if you can construct an argument for yourself why line A has to be parallel to line C. All right, let's go through the argument. Now remember, we start by knowing that A is parallel to B. So I'm going to say, because A is parallel to B, I'm going to use measure. Measure of angle 1 equals the measure of angle 2 because Whoops, that doesn't even mildly look like because. In fact, I'm gonna start to abbreviate, I think, the word because with B/C, because angle 1 and angle 2 are alternate interior angles. All right, so that's easy enough. Now we can also say, because B is parallel to C, measure of angle 3 is equal to measure of angle 4 for the same reason. And by the way, saying something like that in a paragraph proof is perfectly acceptable. It's perfectly good. There's no need for me to say, because they're alternate interior angles. I'm just saying, hey, look back to what I just wrote. Just take it right from there. So 1's congruent to 2, and 3 is congruent to 4, because both situations represent pairs of alternate interior angles that are created by parallel lines cut by a transversal. But somehow, I really want to get 1 and 4 related. But, I always like to use that word, but measure of angle 2 equals measure of angle 3 because they are vertical angles. So, by substitution, now think about this. By substitution, we know 1 is equal to 2, and 2 is equal to 3, so the measure of angle 1 must be equal to the measure of angle 3. Right? So 2 is equal to 3, they're vertical angles. So since 1 is equal to 2, 1 must be equal to 3. And I suppose maybe I should have been able to say 1 is equal to 3 right away because they're corresponding angles. I didn't, so I'm making the argument a little bit longer than I have to, but that's okay. We don't have to get to the finish line the fastest. We just have to get there with a proper train of logic. All right, so 1's equal to 3, okay. And again, by substitution, now I can say that angle 1 is equal to the measure of angle 4. Because again, I know 1's equal to 3. I know 3 is equal to 4, right? So now 1 must be equal to 4. But now I have it, right? 1 and 4 are alternate interior angles that have been created by these two lines cut by that transversal. And I can now finish it, so A must be parallel to C because a pair of alternate interior angles are equal. Again, I'm a little bit disappointed that it took me one extra step. That just gets into like how efficient the proof is. Again, the proof could have been a little bit shorter if I said 1 is congruent to 3 because they're corresponding angle pairs, and then 3 is congruent to 4, or I could have said 1 is congruent to 2 because they're alternate interior, and 2 is congruent to 4 because they're corresponding. Either way, I threw an extra angle in there that I didn't need to. That's all right. Again, getting to the finish line is more important than getting to the finish line faster in geometry. But still, take a look at the proof. It's kind of neat. And it uses both facets of parallel lines, i.e. we use parallel lines to establish angles are equal. And then we turn around and we use the fact that angles are equal to establish that two lines are parallel. This also shows, though, a broader sense of things, though, or a broader principle, which is if we have two lines that are parallel to the same line, i.e. A is parallel to B and C is parallel to B, then A is parallel to C. Okay? It's called the transitive property of parallelism. We haven't talked a lot about the transitive property of anything, but parallelism is transitive. If A is parallel to B and B is parallel to C, then A is parallel to C. All right, let's move on. Okay, now the final piece is that we have to be prepared to use what we've been working with in terms of triangle proof and also bring parallel lines into it. So let's take a look at this last problem. Exercise number 5. In the triangle below, AC and DF bisect each other at E. We would like to prove that AD is parallel to FC. All right. So before we even get into A and B and C and all of that, let's make sure we got it. We've got this line segment and this line segment bisecting each other. And that's enough now to be able to say that FC is parallel to AD. Okay? So let's kind of walk through this proof together. Letter A. State all pairs of angles, if proved equal, that would let you conclude that AD is parallel to FC. I'm going to mark that thing that we're trying to prove in red, as we often do. Marking things as parallel, oftentimes you use little arrow markings, so I want to prove that FC is parallel to AD. What two angle pairs, and there's two angle pairs, could we use to prove that these lines are parallel to each other? All right. Well, if we showed that angle F was congruent to angle D, so if somehow we could show that this was congruent to this, that would be a pair of alternate interior angles. But as well, or, big or, it's not an and, we don't have to do them both, if we somehow showed that angle C was congruent to angle A, if somehow we showed that this was congruent to that. Okay. Now remember, we don't know that these angles are congruent. There's nothing in the givens that have told us that these angles are congruent. Okay? That's something that we need to prove. So let's take a look at part B. How can you prove that these angles are congruent? How in the world, and maybe let's just do this. Let's get rid of that. Delete. How can we simply prove that angle F is congruent to angle D? How can we do that? That sounds like a CP/CTC proof, right? Like if I can prove that two triangles are congruent that contain those angles, then I can prove that the two angles are congruent because they're in corresponding places of the triangles. So I'm going to prove triangle, let's go FCE is congruent to triangle DAE. I'm not sure how yet, but I'm gonna prove that the triangle up here is congruent to the triangle down there. And then I'll use CP/CTC. All right? And I'm not sure why, but today I'm feeling a lot like paragraph proof instead of the T-table proof. So let's jump right into it. And let's start to prove that those two triangles are congruent. Now, take a moment and think about how we're going to go about proving that. What is it about the one given we have? We have one given, which is that AC and DF bisect each other at E. That one given should be enough. Think about that for a moment as I circle the given. And as I go back to blue. All right, well, let's outline the proof, okay? And I'm going to outline it down here. I've got the diagram reproduced. Okay? So I know that these two bisect each other. What does that tell me? It tells me they cut each other in half. So I know those two segments are equal. I know those two segments are equal. Think about it. I've got side, 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 angle, angle, side, angle. And right now I've got a side equal to a side and another side equal to a side. Where does my angle come from? It comes from that vertical angle pair right there. I think I'm going to give those angles some names because that'll make my life a little bit easier. I'll call this angle 1 and angle 2. Let's do the proof. All right, this is going to be simple. Okay, since AC and DF bisect each other, that tells me that AE is congruent to CE and FE is congruent to DE, period. All right, side and aside. Angle 1 must be congruent to angle 2 because they are a vertical angle pair. All right, but that's enough to prove those two triangles are congruent. So, triangle FCE is congruent to triangle, be careful, F goes with D, C goes with A, E goes with E, so triangle DAE by side angle side. All right, now I know those two triangles are identical. Now take your pick. Either F is congruent to D or C is congruent to A. It doesn't matter. I'm going to stick with the F and the D. Angle F is congruent to angle D by CPCTC. Now I can say since an alternate interior angle pair is congruent, FC is parallel to AD. Isn't that awesome? All right. Again, let's recap the proof because it's kind of neat, right? We know that these two segments bisect each other. Because of that, this is congruent to that, and that is congruent to that. Finally, we've got a vertical angle pair that's also congruent to each other. Vertical angle pairs always are, because we've got now a side congruent to a side, another side congruent to a side, and the angle in between them, the included angle, congruent. We can now say these two triangles are identical. Because the two triangles are identical, we can say that this angle is congruent to this angle. By CPCTC, corresponding parts of congruent triangles are congruent. I feel like I should be conducting an orchestra. And because these two angles are alternate interior angles created by these lines cut by this transversal, beautiful job, right? Then I can say that these two line segments are parallel to one another. It's kind of a nice, clean proof. All right, let me step back, give you a chance to write down anything you need to, and then we'll wrap up the lesson. All right, let's do it. So, what we saw today was actually amazingly important, especially for future work we're doing. And that was what I would call the converse, or the converses, of parallel line properties. Parallel lines properties say when two lines are parallel, alternate interior angles are equal and corresponding angles are equal. The converses say that if you can show that even a single pair of alternate interior angles are equal, then the two lines that were cut by a transversal that created those alternate interior angles must be parallel. Likewise, you can say the same thing about corresponding angles. If a single corresponding angle pair is congruent, then the lines that created those corresponding angle pairs must be parallel. This is going to be really, really important when we get into the next unit, not the next unit, I'm sorry, but actually unit number 5, and we work with a lot of things like parallelograms, rectangles, rhombuses, or rhombi. Then we're going to really want to be able to prove that lines are parallel, and we're going to need those angle pairs to do so. All right, but that's for a later lesson. For now, I'd like to thank you for joining me. for another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.